and see you all, albeit virtually. Michael Maloney, the AIP CEO, apologized that he's not able to welcome you today. He's in a board meeting where they're discussing how to manage any increase in occupancy in the building, in the AIP building in the coming months. To be honest, we never kind of thought it would last this long. We thought a few weeks, maybe a month. And now we're looking at not anywhere near full occupancy till the end of the year. So that's kind of going on. Our staff has coped remarkably well, all things considered, through this. And as far as we know, not a single one of the AIP staff has come down with the dreaded lurgy. Kind of hope that that's true of all of you guys and your families as well, that this summer has not thrown you additional curveballs besides having to do your internships remotely. Anyway, I'm really pleased that we're actually having this symposium. At the beginning of this pandemic, we really were quite concerned that it wasn't going to happen this year. And to be fair, thanks to Brad and his team, and we should thank them, because if it wasn't for them and all the hard work they did reaching out to mentors and other folks and making the arrangements and getting everything together, we wouldn't have been able to do this. So kudos to you, Brad, and everybody else on your team for really making that come together. It was really important, for us, and I'm sure for you too, that we were able to make this work. I'm a great believer in internships. I think they're a very fundamental part of your undergraduate, your education process. I ran an internship program for NASA, or the internship program for NASA, for years, and it was the most fun program I actually have run in many respects. And it's one of those kind of opportunities that you have to broaden your scope, to create an opportunity for yourselves going forward. And one of those things that really sets the stage for you for the next steps in your career. So I kind of view it as being almost a critical part of any undergraduate career these days, is to be able to do something exciting and fun in the summers that also kind of pads your CV and prepares you for next steps. While this internship this year may not have been exactly everything you hoped for at the beginning of the year, I hope that the experiences you've had have been really enjoyable and pleasant and exciting and fun. And I'm looking forward very much to hearing about just how much fun you had this summer, albeit a little bit more constrained than we would have hoped. So with that, I'll pass back to Brad.
Thank you, Steve. And that's an excellent setup. So first and foremost, I wanted to congratulate you all. You have done something that we've never done before. We've never had a virtual internship class. Congratulate each and every one of you for doing a fantastic job. I had a set of expectations going into this summer about what it was going to be like, and you vastly exceeded them. So congratulations. It's not easy to do an internship. It's even less easy to do an internship virtually. And it's the least easy to do an internship virtually with people you've never met or barely met. So congratulations to you all. And so AIP is a long history of working in the education sphere and supporting students. This program itself is over 20 years old, which is great. And I'm really happy that we were able to continue it despite all of the unexpected things that might have tried to get in the way. So thank you, AIP, for doing this. And more importantly, to the donors that really helped to make this possible, I want to do a shout out and thanks to both the donors and the mentors. And as you know, the mentors, they spend an awful lot of time with people, helping people, and rarely do they get mentioned. So I just want to make sure I reach out to them and say thank you for doing everything that you could to make this summer great. And one of the reasons we do the internship program is there's lots of really fantastic intern programs with NASA and NIST, and normally they all don't get canceled. But one of the reasons that we do an internship program at SPS is that our program is unique. And so you might have noticed that all of you aren't at the same site. So some of you are working on science policy, some in education, some on astronomy, some at national labs like NIST and NASA, some working with AIP member societies. And it's the total collection of all of your experiences that you've shared throughout the evening fun events and the talking with each other and interacting with each other that makes it so that while you may have worked at, let's say, NASA or for science policy, you have a really good sense for what it's like to do these other internships as well, so that you realize about the true breadth of all of the options that are available to you with a physics or astronomy degree. So it's my hope that A, you had a good time, B, you learned some things that you didn't think you would learn, and C, that you stay connected to the people that you've made this summer, because these people that you've been in this internship with, they're your colleagues, your friends, people you'll know, and you'll be interacting with them and communicating with them for the rest of your lives. So I just want to say thank you, and I'm really excited to hear your talks. There's going to be a lot of really great stuff going on. So I think I'll hand it over to Kayla. And
hey, Brad, can I say something?
Of course.
First, I want to add, actually, I don't know if Brad mentioned this to you guys, but I wanted to add a thank you to you as well, because in doing what you've done this summer, because you're not traveling and staying in the DC area, we were able to use the funds that were released by your abilities to work remotely to provide needs-based scholarships to a bunch of undergraduate students to be able to continue their studies. So inadvertently, perhaps, you guys have made the summer and fall much easier for a bunch of undergraduate students working in the physical sciences. So thank you very much for your contribution.
Thank you, Steve. Kayla?
Hi, thank you. I'm Kayla Stevens. I'm the SPS Programs Manager, and I had the pleasure of overseeing the summer internship. And just like everyone was saying, like, we could not have had this internship without the mentors, our supporters, and you, the interns itself. You are what makes the program, and we are truly grateful and appreciative. And we're all looking forward to the presentation. So I also have the pleasure of introducing you all. So we'll go ahead and get started. The abstracts and the times are in the chat if you would like to look at those and follow along. At the end, we will also have time for questions after each presentation. So through the presentation, if you come up with a question, just put it in the chat and we'll answer it right at the end. So let's go ahead and get started. We have our first presenter, our AIP Mather Policy from John Carroll University, Kyle Blasinski. You may get started whenever you're ready.
Okay, let me get this pulled up here. Can everybody see that? Kayla, give me a thumbs up. Perfect. Okay, hello, thank you for that introduction, Kayla. Like she said, my name is Kyle Blasinski, and I was a Mather Public Policy intern this summer, working on the virtual Capitol Hill. So we're getting through the who, where, and why. Again, I'm Kyle Blasinski, I'm the intern, and I worked this summer for Representative Bill Foster in the United States House of Representatives, where he represents the 11th Congressional District of Illinois. It just so happens to be the only sitting PhD physicist in Congress. So you might want to ask, what are all these physicists doing in Congress? Well, I can't speak for Representative Foster, but I ended up there thanks to the generosity of John Mather, who was also a PhD physicist and Nobel Prize laureate in physics, who had the foresight to realize that STEM professionals and physicists and those in the natural sciences have a lot they can contribute to the public policy discussion. So through his generosity and foresight, I had the opportunity to do just that this summer. And as a physicist, a quantitative guy, we know it's all about the numbers. So I figured I'd start off with some numbers just summing up what I did this summer. So I had the opportunity to help name a post office, write several letters of congratulations to students and staff members at national laboratories in the district and around the 11th District of Illinois. I attended 14 different telebriefings and reviewed 31 pieces of legislation that came across Bill Foster's desk. And of course, that quantitative information doesn't mean a lot without any understanding of what it means. So what does all that fancy number summarization mean? In short, that I read a lot. But if we want to get into the nitty-gritty, focusing on those two big parts of my job, co-sponsor memos and briefing memos, we can start with the former. And when I refer to a co-sponsor memo, I'm just referring to the act of co-sponsoring a piece of legislation in the House of Representatives. So it's one of the easiest ways to get a bill or a piece of legislation attention in the House or in the Senate, is to get your colleagues, your fellow representatives to sign on and put their name to that bill and say they support it. So an interest group might come to us and say, we support this bill, you should support it too. Or a colleague that's written the bill might do the same. So if that request is put into our office, then it works through our internal channels and hopefully eventually makes its way down to me, where I start the process of memoing the bill. And like all great things, memoing a bill for co-sponsorship starts with a lot of research as to why the bill was proposed, what problems is it trying to address, things like that. And after that's done, I have some context. I can move into actually reviewing the bill, reading the piece of legislation, seeing what it actually does, where funding comes from, where funding goes, things of that nature. And the hardest part for me afterward is then summarizing all that research, that big long piece of legislation, into a couple of pages that a congressman can read in a 5 minute meeting in the afternoon. But then my favorite part after that difficult summarization is I actually got to provide recommendations as to whether or not I thought a congressman should co-sponsor the bill or not. I put a little star there because if I was wrong, someone would correct me. But after those first couple of weeks, I was wrong a lot less often. So something to be proud of. And then briefing memo is another big part of my job. We're a little more straightforward, where an interest group can hold a roundtable or a policy discussion with policymakers to advocate for a certain position. So I would just watch and tune in, listen in, and record it so I could watch it again if I need to. Similar to the co-sponsor memos, summarize what was talked about, and then if those people in that talk or that roundtable had any recommendations for policies, things like that, I would report that back in a memo to our office as well. I had a couple of favorites. My favorite bill that I got to review is the RISE Act, which was meant to put billions of dollars into federal research at different federal agencies like NASA, NIST, all those places, all the other interns work. So it got me a lot of love from those guys. And then my favorite briefing was probably this briefing from R Street Institute on the pharmaceutical supply chain globally, where we get drugs, where we get active pharmaceutical ingredients, things that I would never think about as a physicist, but have really important implications for foreign policy and trade policy. And although I had favorites and I had a lot of fun, I can't help but ask whether or not this work was meaningful. So let's take a look at what are the things that are meaningful to Americans. So when asked, Americans came back with these 5 things, a majority of adults, as being the big problems facing America today. So ethics in government, obviously the coronavirus, healthcare affordability, criminal justice, and unemployment, which can really boil down to these 4 categories. And then looking back at those bills that I reviewed, let's see where they fall into these categories, if these priorities align with the work that I did. And looking at that review, I mean, they did. Over a quarter of the bills I reviewed had to do with government administration and the economy, and then less than a fifth each had to do with healthcare or health in general and criminal justice reform. So I think it's safe to say that people care about the economy, health, and justice, and the government itself. The work I did had to do with healthcare, government administration, criminal justice, and the economy. So I mean, there's a lot of overlap there. So yes, the bills that I reviewed and the work that I did align with the priorities of the American people. So the work was not only fun and educational, it was also meaningful professionally for me, but also legislatively for the country I was serving. The only downside is, of the 31 bills I reviewed, as far as I know, only 1 has become law so far. It's actually made it through the House, made it through the Senate in the same version, and then was signed by the president. And I kind of boiled that down to 3 main factors. 1 being partisanship. Obviously, there's a divide between Congress, congressional houses, and the White House right now. Some bills are just for messaging. They're not always meant to be passed into law. And then a lot of it is just the sheer volume of bills proposed in the House. I think we're approaching 8,000 pieces of legislation proposed right now, so it's just not realistic for them all to become laws. But even at the end of the day, even if 1 in 31 bills becomes law, of the 8,000, that's a ton. And even if everything I did didn't become a law, it was still great, meaningful work that might set the stage for future legislation. So I can't help but be thankful for the opportunity I had this summer, that it was possible, it was meaningful, it was educational, and it was fun. And I have all these wonderful people to thank for that. So while you read their names, because there are so many, I'll happily answer any questions that you might have.
Great talk. So we have a couple of questions from the audience. First question is, how did you interact with other staff members in Rep. Foster's office?
So our main form of communication, like a lot of people right now, I think, is just email. So if I just had a simple task to do, it's just emailed over to me with whatever background I might need to carry it out. And then we also had weekly staff meetings where everybody in the DC office would get together and talk about legislative priorities for the week, different bills that were coming for a vote, things that I was doing, questions I had, stuff like that. So we had a combination of Zoom meetings and emails.
Follow-up question, was it ever stressful or was there ever any like tension in any of the conversations?
Not really. It's surprising how like cordial people that work in the government are. Maybe it's a House of Representatives things because it's the lower house or whatever, I don't know. But everyone is very friendly and they joke around, and it's not all like suits and ties and, you know, weird stuff like that like you might see on TV or like House of Cards or anything like that. But so no, not for me. It wasn't really stressful or tense or anything like that.
Great. Next question. What was the most interesting telebriefing you attended over the summer?
Oh, so that's what I alluded to on that one slide, was the one on the pharmaceutical supply chain, which, because it's just so outside of the ballpark of physics, it's something I would never think about. Where do drugs come from? How do we make drugs in the US? But it was just so interesting because I think, especially with coronavirus and issues of PPE, things like that, people were concerned about where these things were coming from, and it has huge implications for our day-to-day lives. So it was really interesting to just do something totally outside of my normal field of view.
And one quick question, one more. What is the most valuable skill, expected or unexpected, that you picked up over the summer?
Technical reading of non-scientific work. So you think about like a scientific paper, there's a lot of skipping around, and you have the background in that if you read like a physics paper, if you're an expert in whatever field. Translating that right over to policy reading, to reading a piece of legislation, I mean, that's a whole different form of technical reading. So I think that was, I think, to be expected, but a skill that I didn't necessarily have perfected that I think is a lot more finely tuned now that the summer's over.
Great. So great talk. There's some additional questions and we'll try to get those answered in the chat. So thank you very much.
Thank you, Brad.
Thank you, Kyle, for that wonderful talk. And now we have our APS Education and Diversity intern, Madison Swartz from the Colorado School of Mines. You may begin whenever you're ready.
Hi, I'm Madison Swartz. I was the APS Education and Diversity intern this summer, and I'm going to talk to you a little bit about what I did and why studying people and diversity is difficult. So a little bit about me. I'm at the Colorado School of Mines, and I'm someone who's been deeply invested in my physics community ever since my freshman year. I've served on a bunch of different leadership positions. I've been really active in outreach my entire undergraduate career. So things relating to equity and inclusion are things that were already really close to my heart, which is why I was initially interested in this internship. So my job, initially what I thought it was going to be, seemed pretty straightforward. There's a set of graphs and statistics that needed to be updated for the 2018 graduating school year that relate to different underrepresented groups in physics. And my job was to update those. I assumed that this was just going to be sort of pulling numbers off a database and plugging them into Excel and making graphs, but it very much was not that. So this is the database I was working with, the Integrated Post-Secondary Education Data System, otherwise known as IPEDS. And this table shows the people graduating with a bachelor's degree in physics every year. Or this particular one shows the 2018 graduating year, broken down by race and ethnicity. The big thing I immediately noticed, there's only 6 categories of different racial ethnic backgrounds. And if you don't fit into one of those, you're thrown into one of these bottom 2 categories. And this caused a lot of really weird inconsistencies in data. Sometimes when we need to take a percent, like for example, the percent of women in physics, we would look at something like take the number of women divided by the total, but if you're looking at an underrepresented racial group, you need to take out the non-residents because that was counted as a separate group. And there were some graphs where, so there were some where you had to do that, some where you didn't. Some graphs we decided to group together Native Americans into like one category, which included American Indians, Alaska Natives, Native Hawaiians, and other Pacific Islanders, which means that by our data, an Inuit person from Alaska is totally indistinguishable from someone from the Philippines, which I thought was really weird. So not only was a lot of this stuff just, it felt weird and unethical, but it leads to bad data. So this is that 2 or more races category, and you can see that it has almost 400 students in it. And when you're talking about the number of undergraduate physics majors, that's huge, especially if you're looking at these numbers for Black or African American students, American Indian or Alaska Native, and Native Hawaiian and other Pacific Islander, where the numbers are lower than 400. So if you list yourself as more than one identity, then your identity is sort of thrown in this black hole of the 2 or more races category, and all of that information is totally lost to us. And it means that where we might be seeing upward trends, we may be seeing stagnating or downward trends instead, which is, I think, bad science. So there wasn't much I could personally do about this because this is just the way data is nationally reported. But it was something I felt really uncomfortable with. But that was just the start of my summer. I ended up finishing my job really early, and this was all happening sort of in the same space as the Black Lives Matter protests. We're all quarantining at home. It was a really good time to be working in diversity, equity, and inclusion. So I got to attend the From Passion to Action webinar, which is about being a Black physicist, which was amazing, and I learned so much. And I got a chance to do a literature review where I got to read up on Black feminist theory, and physics identity papers from the physics education research community, as well as papers about informal physics education programs, which really hit close to home to me as someone who has a background in these things. And I started to realize that physics education researchers are doing extremely interesting work that is extremely relevant to me, and where there are lots of really open-ended questions that have yet to be answered about how we're keeping students in physics and how we're treating them while they're there. So I wanted to learn a lot more, and so I kept reading papers. I attended the conference for the American Association of Physics Teachers and PERC, which is the Physics Education Research Conference, and learned even more about the amazing work that PER is doing. And so I'd like to leave off with this Brian Greene quote, that sometimes attaining the deepest familiarity with a question is our best substitute for actually having an answer. And that's how I felt a lot about this summer, that more than I learned about the actual data that was there, which is what I thought I was going to learn about, I learned about what questions we're asking, why we're asking questions that way, and what are maybe some better ways we could be doing or posing questions and building these frameworks in the first place. I also learned that the physics education research community has done a lot of work that I just kind of didn't realize was there until it was pointed out to me. I also learned that physicists have the skill sets to do this learning. These were technical papers and they were amazing. So yeah, thank you. Are there any questions?
Great talk, super awesome. We have a couple questions from the audience. First question is, how did your work intersect with the work done at the Statistical Research Center?
I don't know about the Statistical Research Center, so I'm not entirely sure what is meant by that.
That's fine. The, AIP has a statistical research center, so they do statistics where they talk directly to departments and ask departments to provide information. So.
Oh yeah. So I did actually hear a little bit about that. That's where I learned about this 2 or more races category and how it's affecting, potentially disproportionately affecting Black students. It's something that I couldn't really talk about because it's not publicly available information like IPEDS is, but that's where we started learning about these sort of data discrepancies was from them.
Great. Second question. How does your view of, did anything come of the data black hole problem? Was this process encouraging or discouraging?
There wasn't really much, like, again, this is national data. I couldn't really, like, the disaggregated data that has those sort of like multiple answers isn't available to me. So I can't really do anything but point it out at this point.
Kind of follow-up question kind of on the first two. So you had mentioned a little bit about how it's important to kind of, we should be asking the right questions, right? And so with all the things that have happened in the spring and the summer with Black Lives Matter and diversity, equity, inclusion, did you propose or think at all about so kind of new questions that should be asked or new viewpoints that should be gathered?
Yeah, so I actually applied for an APS mini grant with my mentors for this summer about looking more into the connection between physics identity and outreach programs, because that's one of the best predictors of student retention we've seen. And I think actually making that direct connection is really interesting. I've also become really interested in sort of intersectional identity and framing questions, asking questions through that lens, and not just trying to gather sort of straight up data and get more on each person's individual identity.
Okay, and then great answer. And then one last quick one. You mentioned the intersection of multiple races, or did you also look into the intersection of race and other identities? For example, the number of Black or Hispanic women or men?
Yeah, so a couple of the graphs relate gender and race like that. One thing we don't have is data on queer people at all. There are tables and statistics in there about like that include both of those.
Okay. Wonderful talk. We're out of time for questions, but there's a couple more, so I'll let you answer those in the chat. So again, congratulations.
Thank you, Brad.
Thank you.
Thank you, Madison, for that wonderful talk. Next, we have Joseph Dees, our APS Bridge Program intern from the Henderson State University. You may start whenever you are ready.
I hate this little thing. All right, so my name's Joseph Dees, and I worked with the APS Bridge Program through the help of the Society of Physics students, and I worked on methods of raising awareness and increasing participation of underrepresented minorities in physics PhD programs. My mentor was Breon Clash. So where's the problem? Well, part of the problem, you can kind of see it in the graph, but I'll explain it a little bit. When you look at underrepresented groups in the US, then 33% of college-age Americans fall into the underrepresented minority populations. But if you look at the statistics in this graph on the right, you'll notice the blue over here has the bachelor's on an increase over the past few years, but it still is significantly lower than that at only 13.5% of the bachelor's degrees in physics being awarded to underrepresented groups. That is even more evident when you look at the master's, and there's only 11% of the master's degrees in physics that have been presented to underrepresented groups. But there's a significant drop when you begin to look at the underrepresented groups getting PhDs in physics. And so that's where the biggest problem we have right now that I was to address this summer is, where is the big disconnect now? Well, part of it is motivation. You know, for many of us, when we walk into a classroom and we look around at the other students that are in there with us, or even look at the professor teaching, then we immediately feel like we belong. We immediately feel like we have something in common with them. A lot of underrepresented groups don't. So as soon as they walk into that classroom, they are immediately socially and academically isolated. With that isolation becomes a growing sense of imposter syndrome, which, don't get me wrong, most of us face that on a day-to-day basis. But when you don't have a group of peers or a group of mentors or people that you can't feel like you relate to, then that only compounds the problem even more. The next issue here is a lack of mentors. With a lack of PhDs in physics being awarded to underrepresented groups, then it becomes extremely difficult to find mentors. That is only compounded when you look at campuses and again, you're looking for community support, and you don't have community support because there's not that many people that look like you, that are from the same background. And then finally, funding. Funding is a very big problem. But you know what wasn't mentioned in all of this? They have the talent to be there. They've done the research. They've put the hours in, and they have the ability to get the PhDs. So what can we do about that? What are some action items that we can do to make this better? One of the key factors in success, having looked at successful graduates and what made them stick with it, is mentoring. With a lack of underrepresented groups that can be a mentor, it puts an additional burden on the rest of us, not only to try to mentor those that don't necessarily fit into our social group, but also to maybe reach out to those that may be attending a different university and become a mentor for them. You don't have to just be a mentor in person. Sometimes you can be a mentor virtually, as this summer showed us during our internship. More important is a sense of belonging, and that's something that we all can have a part in, because how you react to that underrepresented group when they're in front of you will determine whether or not they consider you to help them, to be someone who wants to welcome them in, and then not letting them get lost in the pipeline. That's another big problem, because when we see high-level work being turned in on an undergraduate level, then why aren't we taking the time? Doesn't matter if they're your star student or not. Why aren't we taking the time to tell them that they can fit in, that maybe they should be the ones pursuing a PhD and helping them along those ways? Well, those are the key factors. Where can some of these be found? Summer bridge programs, there's many of those across the nation, and also the APS bridge program, which is where I worked this summer. What is a bridge program? That's a good question. I'm glad you asked it. Well, it provides several things. It provides mentorship. It gives you accountability, somebody to go back to. It provides you a mentor who's also going to help you with your research opportunities. And for example, the bridge program, the APS bridge program, actually will take your application and forward it to several different graduate degree granting institutions without any fee to you. So that in itself is a form of funding. The target audience for most of these, you have to already have your bachelor's degree and you have to have a desire to pursue a PhD. A lot of times you have applicants that apply to these programs that have been turned down from going to grad school, but that is not the only requirement. You can be someone who just hasn't had the opportunity to apply to grad school as of yet. Okay, so if it exists, why isn't the situation improving? If we already have these programs in play, why don't we see a difference? Well, the APS bridge program is starting to see its first consort graduating with their PhDs. There's a 3 to 5 year graduation cycle involved. But the other problem is there's not enough applicants. So we need to encourage additional applicants so that we can see better results from these programs. How do we get more applicants? Well, when I talk to several different peers of mine across several different universities from different underrepresented groups, the first thing I ask them is, why didn't you decide to go after your PhD? And they said, well, we didn't get accepted and we don't know really what to do now. They didn't. So then I asked them if they knew what a bridge program was or they knew about the APS bridge program. And their answer was, I don't even know what you're talking about. Knowledge of the program is where a lot of times the disconnect happens. The knowledge of the program can come from early mentorship. When you, as I said earlier, when you have up and coming sophomores and juniors and seniors that have the drive to become a PhD student, why don't you mentor them? Tell them where they're at. Help them get to where they need to be. Help them feel like they belong. But the other thing I noticed when I looked through the pool of applicants, then a lot of the degree granting institutions that have granted a high number of underrepresented minorities degrees in bachelor's in physics, some of them aren't even having anybody apply to the program. So reaching out to them and creating a partnership so the knowledge of the program again is spread to them is crucial in the success of the program. So my challenge to you all is to not let those underrepresented groups become somebody that you never see again, that just fall by the wayside. Become the change you would like to see in the world and make a difference in their lives. Thank you for the opportunity for serving this summer. I want to thank the Society of Physics Students programs, the APS programs, and especially my mentor, Brian Clash, and of course, Brad.
Thank you very much, Joseph. I appreciate you. We have time for one quick question. So the first question we got was, how did you respond to the Team Up report? Did you look at that at all in what you were doing this summer?
I actually did not come across the Team Up report until near the end of my summer. It was a very informational piece of research, which actually quite lined up with what I'd already found out earlier in the summer. And many of the different statements that you've seen in this presentation are mirrored in that report. That report is based on undergraduate work. I think it would very well align with the similarities of why underrepresented groups don't complete their PhD.
Thank you. And we actually have a bunch of other questions. Joseph, I'll let you answer those in the chat. So congratulations and thank you for a wonderful talk. Kayla?
Yes, thank you for that wonderful talk, Joseph. Up next, we have our APS Careers Intern, Jack Moody from University of Massachusetts, Amherst.
All right. Can everyone see my screen? Take that as a yes. All right, good morning, everyone. As Kayla introduced, my name is Jack Moody, and today I'll be presenting Helping Budding Physicists Find Career Success. So first, just a little bit about me. I'm a rising senior at UMass Amherst studying physics and applied math, and I'm also an Army ROTC cadet. In terms of my experience and background, I absolutely love career development. I participate in a large variety of mentorship programs at UMass, where I help fellow first-generation physics and math students help find success and help find mentorship opportunities and help get where they need to go. It's going to be my third year as a freshman RA, and of course, I'm the 2020 Society of Physics Students APS Careers Programs Intern. So first, just a little bit of background before starting my internship. During the start of the shutdown for COVID, I actually reached out to MidHat and asked if there's anything I could do to help. And she recommended going and contacting David Voss at APS News and trying to write an article for them. So what I ended up doing was I published an article in the June 2020 APS News back page that was all focused around helping undergraduate students stay motivated and productive during COVID-19. So if anyone is still struggling or has any students that's struggling, I highly recommend them going and checking out this resource. As for what I actually did when my internship started, It all kind of began with the physicist profiles. And really redesigning the webpage. The physicist profiles is a resource we have at APS Careers that goes over 60 plus interviews we've done with a variety of physicists from a wide array of backgrounds, and it goes over interviews we've done with them, their career path, how they got there, and any advice that they would give to undergraduates. The problem, and you can see the original website here, is that it was just a giant list of names, and you couldn't tell what anyone did without actually clicking and reading all of the articles, which isn't the best for retention and having people actually utilize it. So what I did was I went through and read all 60 plus profiles and tried to come up with a schema in order to create a more engaging interface. So what I did was I read all 60 profiles and kind of fit them all into 4 bins, if you will. And those 4 bins included careers in academia, public service, the private sector, and national labs. From there, I did a little bit further. I went a little bit further and actually categorized everyone based off of the degree that they held at the time of this interview. So for example, if you yourself are interested in a career in national labs, you click on that the national labs page, and then you get presented with this, which shows all the different people we have interviewed with bachelor's degree, master's degrees, and doctorate degrees. So you can go and read those resources and figure out how they got to where they're at, as well as showing the common career paths that we have for a more generalized overview of how to get into that career. Highly recommend anyone checking this out. Really like how it came out. Up next, I participated in the Shape Up email series. This is a brand new product being designed by APS Careers that was focused around creating targeted emails to help people find career success or help find success based off of where they're currently at in their career journey. So how we did that was Midhat and I at first developed 3 different audiences: people that were just trying to find careers out there in physics and see what's available to them, people that are actively searching for grad school, and people that are actively searching to find jobs. After developing those 3 audiences, Midhat and I got to work actually writing all these emails and getting them ready for launch with the communications team. You can actually see one of the emails that I wrote up on the side of the screen right there for people finding out grad school is right for them. Some early statistics, there was a soft launch for the Shape Up email series about a week and a half, almost 2 weeks ago, and we've been able to get some preliminary data back. So far, 46 people have signed up for Career Explorers, 38 people have signed up for the Job Seekers, and 33 people have signed up for grad school. Highly recommend checking it out. There's an open rate of over 70% so far, and we're really excited to see where this program goes in the future. Finally, I was able to host my own webinar and write up a webinar for the APS Summer Webinar Series that was focused around the APS Careers website and showing all the different resources that we have on it for undergraduate students and their advisors, and how to begin fostering a sense of career development and the importance of it all the way from freshmen through people walking out the door with their undergraduate degree, and provided specific examples for how to find those resources and how to utilize them properly. When we presented it live, it was attended by 112 people, which is really great audience engagement. We had some really, really great questions. And it was absolutely the highlight of my summer being able to give this talk. And if you'd like to view it yourself, feel free to go to go.aps.org/summer webinars, or find it on the APS YouTube channel, APS Physics. It's titled A Guide to Career Development. Overall, some reflections and lessons learned. I've always loved writing, so it's a great opportunity to really recultivate that passion and get a lot of experience with it. And learning how to work in teams where you're not always working on the same thing. So being able to work with both the comms team and the web development team was really great exposure for me, and being able to see what it's like working in such a large company. As well as applying first principles. This was not a traditional physics internship in the sense of it being research-based. So this required a lot of being able to abstract my physics background and apply it to new tools and apply it to a new set of challenges that was really, really rewarding for me. And of course, I learned a lot about communication and being able to talk to people and all those different things. And overall, I have to give thanks to everyone you can see here, and for all the interns, especially Midhat, Crystal. Thank you all so much for this amazing opportunity. It's meant a lot. Thank you.
Thank you. Great talk, Jack. I really appreciate you too. And you did a wonderful job. So we have a couple quick questions. So SRC does the PhD plus 10 project, and they also put out initial employment data. Did you look at all, or did you reference that at all in your work?
So my specific internship wasn't really around actual employment data. It was about finding ways to get people to see what's out there. So it's more focused on showing people the resources and what's available to them, and not so much about the actual current statistics that are out there.
Great answer. And so focusing on the work that you did this summer, I know you took all of the talks and you categorized them. How difficult was that to put it into, because you chose, I think, 4 categories, is that correct?
Yes.
Was 4 is an arbitrary number. Was it hard to come up with that number and to do that?
Yeah, it was pretty difficult because there was also times where people overlapped. So they were a professor, but they also worked for NASA, or they worked for NIST or Oak Ridge, things like that. So actually, there are some profiles that are in multiple categories. So it was difficult. The biggest one right now is public service. We have very few people in that. The goal is to actually get more people into that, learning about people that are in the policy world, the politics world, things like that. So it was difficult, but Minat and I were able to get it done.
Well, you did an awful lot this summer, and the resource looks wonderful. So great.
Thank you very much.
Mm-hmm.
I'll stop screen sharing now. I can move my screen. Sorry about that. Thank you.
Awesome. Thank you, Jack. Up next, we have our AIP Mather Policy Intern on Capitol Hill, Paul McKinley from Pomona College.
Great. So can I just get a quick audio visual check, Kayla?
Looks great.
Great, thank you. All right, so good morning, everyone. My name is Paul McKinley. I was one of the AIP Mather policy interns on virtual Capitol Hill this summer, and I was placed in the U.S. House of Representatives Committee on Science, Space, and Technology. And so one of the goals that I had going into this internship was to essentially better understand the science policy pipeline. And specifically, I wanted to get a better sense for the intersection between legislators and folks in the research community. And so I'm going to be talking about one of the legislative projects that I worked on that explored this intersection. And so just a bit of background about the House Committee on Science, Space, and Technology, also known as House Science. It was founded around the area of the space race. And the point that I want to make is that House Science is a standing committee. So that means that it has its own staff, its own office, and is typically allowed to take a more deeper dive into specific policy issues. And for our committee, that applies to most non-defense related research and development. And so that jurisdiction is further split amongst 5 subcommittees. And over the course of the summer, interns typically have the opportunity to work on a myriad of projects in each of these different subcommittees. But one of the longer term assignments that I had was working with the Research and Technology Subcommittee on legislation for the National Science Foundation. And so the type of bill that we're talking about here is authorization legislation, or reauthorization in this case. And so these bills can kind of do 2 main things. They can either create a new federal agency or program, or continue the operation of existing ones. And they can also set funding levels for congressional appropriations, which, just to be clear, is not quite the same as providing funding directly. It's more setting guidelines that the Appropriations Committee can then take into account. And so the National Science Foundation, or NSF, as an independent government agency, requires this type of legislation every few years. And this is important for such a wide-reaching organization like NSF, which funds roughly a quarter of basic research at US institutions. And so for this bill in particular, the NSF Reauthorization Act of 2020, again, it kind of focuses on these 2 main criteria. So on the funding side, as you can see on the graph here, there are significant funding increases over 5 years, from about $7 billion now to over $17 billion by 2025. But it's important to note that the majority of the bill is not focused on funding provisions. The majority of it is focused on identifying and seeking to remedy policy gaps within the foundation itself to better support individuals in STEM education and research. And it also paves the way for entirely new research directions with this last point, in which the bill would establish a new NSF directorate for convergence research and innovation. And so this is sort of a simplified timeline of the bill and its progression. And so there are two main things that I want to point out. One is that we're still fairly early in the process for this to becoming a law. And so many of the later stages are sort of in flux due to the COVID-19 pandemic. But the other point that I want to make is that in green here, stakeholder input is a process that's fairly early in the drafting timeline. And so this was really the part of the bill that I got to work on. And so sort of a what is stakeholder feedback and why is it important? So after initial drafting and vetting of the bill, it's sent out to various members of the scientific community, our stakeholders. And so these are professional societies, universities, graduate student groups, and STEM advocates. And so they'll typically review the bill and submit different feedback for voicing support or giving suggestions for how it can be improved. And so as you can see, we heard back from a number or a majority of our stakeholders with roughly 350 different either suggestions or voicings of support. And it was my job to compile this feedback as it was coming in and then condense down each suggestion into an annotation that could be linked to specific bill text, which would then later be reviewed by staff. And so just to emphasize a few key areas of feedback, we got feedback on every section of the bill, but a few that stood out were the establishment of the new Convergence Research and Innovation Directorate, which would really focus on high-risk, high-reward research that might not be funded by the other directorates. And so there are a lot of perspectives on how to roll this out effectively and what type of funding to provide. And a few sections in which we received a lot of support and some very valuable suggestions on how to improve our broadening participation provision, which as a subject has been a key tenet of our chairwoman's entire legislative and professional career. And so it's very important for our committee. And we also got a lot of support for our provisions on fundamental research. So doing things like requiring ethics considerations ahead of research projects and increasing the number of open data repositories. And so sort of in closing, I think that this bill and the part that I got to work on is really just one example of this critical and dynamic dialogue that takes place in the science policy process between Congress, government agencies, and the science community at large. And I think that COVID-19 has somewhat tragically underscored the need for public engagement in that process as well. And I think we're already starting to see that increase. So I feel fortunate to have had the opportunity to work on this piece of legislation that could enable a widely influential organization like NSF to not only continue supporting US basic and translational research, but really invest in programs that will have long-lasting societal impacts via science and engineering. So thank you to SPS and the folks at House Science. Thank you specifically to Dylan Cohen and Sarah Barber for their help on this project and throughout the summer. And I'd be happy to take any questions.
Great talk, Paul. Fantastic. We have time for one quick one, and then we'll have some other questions in the chat. What is your opinion of the Endless Frontier Act? And could you compare it briefly with the NSF Reauthorization Act?
Yeah, so I want to be careful not to inject my own perspectives on these two bills. It would be something that for specifics, probably staff should talk about in our office. But I think there's a lot of overlap between the two bills. This would be focused more specifically on the operations of the National Science Foundation. But again, reconciling the two bills would be something that would need to happen at one of the later drafting stages between the House of Representatives and the Senate.
Okay, thank you. I appreciate it. And you did a fantastic job on your talk. Congratulations.
Thank you.
Thank you, Paul. Up next, we have Max Dornfest from the University of California, Berkeley, who was our AIP Matter Policy intern at NIST.
All right. Hi, everyone. My name is Max Dornfest. I'm talking to you from Fremont, California. I'm a senior at UC Berkeley, graduating in the fall, and I'm also a research affiliate at Lawrence Berkeley Labs, where I study computational cosmology. Specifically, I look at power spectra and similar analysis of Lyman alpha signal from simulated computations of large-scale structure. So where I worked this summer, I worked at the National Institute of Technology, NIST, but more specifically in the Office of Advanced Manufacturing. The major program, Advanced Manufacturing, has input from departments such as the Department of Commerce, Defense, and Energy, along with multiple agencies such as the NSF and NASA. The main point of Manufacturing USA is to move prototype technology to a mass manufactured scale. So along with this research project, I just told my supervisors that I was interested in writing a paper along with any work they wanted to give me. I started with being really interested in the United States' ability to manufacture supercomputers based off of my research at Lawrence Berkeley Labs. But COVID really changed that. So I also reviewed grants and created industry one-pagers, and that industry one-pager ended up being on healthcare. I ended up looking at a specific institute in Manufacturing USA, NIMBLE, and they focus on biopharmaceuticals. Therefore, when I developed my paper, I decided to take data of the 4-state region around NIMBLE, which is based in Delaware, and I collaborated with 2 professional economists at NIST. We used MC, which is a data aggregation tool that's used by professionals. It takes data from County Bureau of Statistics. The language I used is just Python 3.0. It's pretty normal. The only thing of note is that I use stats models instead of sklearn for analysis. Pandas was used for data handling, and Stargazer is an analog library from R just for nice tables. In terms of analysis, I had 3 prongs of attack. Standard regression, otherwise known as ordinary least squares. It's going to be easy to implement, and it should be my first avenue of analysis. Then regression discontinuity is an ability to look at a difference or the deviation of a regression based off of a time-ordered event. This would be, let's say, the establishment of NIMBLE and the following year. Then looking at the next 3 years of NIMBLE's existence, whether or not it would affect the data in the region, deviating from the mean of either the United States or the 4-state region around NIMBLE. Finally, synthetic control is a really amazing application of Fourier analysis to remove the time-ordered dependence from the data, and instead one is able to create a Bayesian likelihood of any hypothesized institute having an impact anywhere in the United States. So that was a really cool idea. So right now I'm going to present just standard regression results. I went in assuming that they would be highly dependent on what I chose for my models. So I started out small and included more and more variables as I went on. And I'll walk you guys through 3 results. I also wanted to look at both geographic results, such as state-based or county-based differences, and a chronological relationship that I hinted at with the discontinuity study. Finally, there are multiple sub-institutes for other Manufacturing USA places, and I wanted to look at maybe the influence of those in the broader paper in general. So the data, what's important and needs to be taken away from it is that there are 2 independent data sets. One is for industries and one is for occupations. These use 2 different categorical variables for codes for industry or for occupation. And you'll see on the next page what I mean by that. But just understand that NAICS and SOC are the 2. So if we look at the left-hand side, oh, I am so sorry. If we look at the left-hand side, we can see that area is marked by 10 and 34, and this is probably Pennsylvania, or this is, yeah, I think Pennsylvania and Delaware. And industry is for, let's say, biopharmaceutical engineer. And the jobs are not integers, but I do have multiple variables which allow me to understand wages. Also note that I have a variable called location quotient, which will be more important moving forward. Then in occupations, the one thing to note on this page is that my data actually did not include earnings for any year other than 2018. So this is for occupation data, and I thought I would have the change in earnings per year. This was a major limitation that I did not expect. But results were still really great. This is a result with a R-squared result that I feel is reasonably good for social science. And then specifically, I did a Durbin-Watson statistic run, which would look for autocorrelations in my data. Since I picked a pretty simple regression, if you see it's jobs and year based off of location quotient, I'm able to confidently say that this isn't simply because I picked two variables out of my data set that happen to have a high R-squared, but that this is a pretty independent result. Similarly, I looked at both occupation on top and industry on the bottom for areas as categorical variables. And we can look at T10, which is Delaware, and it's the one state with stable signals between the two data sets. All other data sets have a difference in their coefficient, but we can see that T10 is 0.4 something. So this was a really promising start. Finally, the last result I'd like to show you guys with my limited time is called a QQ graph. This shows the distribution of residuals plotted along a 45-degree line. This means that if we expected a normal distribution of residuals, we would hope that we would just have a 45-degree line. Instead, we see a similar structure on the left-hand side for occupations, on the right-hand side for industry. But we can see that these are different graphs, particularly in the hump on the bottom left-hand part. We see the hump is diminished versus on the right-hand side, it follows the 45-degree line longer. My concluding thoughts is that this is a great learning experience. The paper is still ongoing. I have 2 anchor authors on it. I was recently asked to interview by a headhunter for a position on Wall Street. And when he found out that I was also working on an econometrics paper, he was ecstatic, saying that this was exactly the position that I was being asked to interview for. So in conclusion, this was a really serendipitous, great choice, and I am really appreciative of the chances I got to this. So thank you for everyone for the amazing summer. I am so appreciative, and I think I'm over time, so I will ask questions.
Great job, Max. We have time for one quick one. So to paraphrase a little bit, what was the most valuable skill that you acquired this summer, expected or not expected?
That was really interesting. Actually, I think there were so many great ones, like grant review. I was entrusted as an independent adult to look over an entire grant for a large share of money, and that would have been first. However, my supervisor, Robert, who I respect a great deal, told me to start writing meeting agendas for our biweekly meetings. And I found these to just really help my organization. I hadn't beforehand written up bullet points for every meeting I was going to do, and I started doing that this summer, and I have found it endlessly helpful. So that actually I think I'll take with me as a life skill going forward.
Great talk. Thank you, Max, and we appreciate you very much.
Thank you.
Yes, thank you, Max. Up next, we have Samantha Creech from the University of North Carolina, Asheville, our Physics Today Science Writing Intern.
All right, I'm going to share my screen real fast. All right, can you let me know if you can see it okay?
Looks great.
All right. So when we sit down to write an academic paper, we all know what kind of grueling process we need to expect. You have to be thorough, including every detail of your process as you battle to the death with LaTeX, and any literary artistry is essentially slashed by heavily technical writing. Sitting down to write a story, on the other hand, is a totally different beast. Science journalism is the field that stands at the interface between science and society. There are numerous media outlets that participate in science journalism, each of which has their own audience and their own purpose. One such outlet is Physics Today. It targets physicists, so any article in its magazine should be pretty understandable by somebody with a general understanding of the field. PT has a physical print magazine that comes out with monthly issues, as well as an online editorial. Physics Today Online supplements the monthly edition with the daily edition, shorter posts that update readers on recent research or what's going on in the physics community. For the sake of this presentation, I'm going to talk about the process of writing a research update for the daily edition. So the first step to writing any story is to find a topic to pitch. And for me, this was pretty consistently the most challenging part of the process. I much have pitched nearly a dozen mediocre ideas before I started to really grasp what actually makes a good story. It takes some intuition to scan journal abstracts and say, this will be perfect for Physics Today. Finding a story is just as much an art as it is a science. In general, you want your topic to be timely. When you come across an idea, you should ask yourself, why should I write about this now? And in science journalism, the answer is often fairly simple. That study just came out, or that discovery was recently made. But you also want your topic to be new. You don't want to write about something that's been reported to death. One of the studies that I pitched was about neutron stars, and that paper hadn't been written about yet, but neutron stars are a common topic for Physics Today. And in order to merit writing yet another neutron star article, the finding would have to stand out. This one just wasn't particularly groundbreaking. And last but not least, the article has to be important. And I put to the audience because what's important changes if you're writing for, say, popular science versus Physics Today. A Physics Today audience might be interested in learning about nitty-gritty topics like topology. They might also be interested in learning about honeybees, which was one of my successful pitches. If there's a connection to physics or to the physics community, then it may be relevant. So the next step is reporting, which is the process of gathering information for an article. The first step of this is usually to review the literature, which is something that we're all familiar with. Although you certainly won't include all the details of the paper, understanding those details improves your judgment when you're deciding what the reader needs to know. While I've been reading technical papers for a while, conducting interviews was entirely new to me. I ended up interviewing 4 people throughout the summer. And while I never stopped being ridiculously nervous beforehand, I found that normally they went pretty smoothly. The nice thing about science writing is the fact that the people you're interviewing usually want to tell you more. You're not trying to dig a confession out of anybody. You're trying to understand this research that the scientist is really passionate about. Now, the paper usually gave me all the technical information that I needed. The interview is mostly meant to get the human side of the story. For instance, when I was interviewing the lead scientist for my honeybee piece, he told me a story about his father's experience with beekeeping, and that led me to emphasize the ways that his research could help beekeepers. So once the information is gathered, next comes the fun part, which is actually writing the story. And first of all, you want to give your article a story-like structure. It should have a narrative that takes you from beginning to end. The beginning of the piece is called the lead, and it should give the reader a reason to keep going. Let them know what the article is going to be about, but don't give away too much. Keeping a little suspense is a great way to spark their interest. And throughout the piece, you should also be writing with your outlet in mind. For Physics Today, that means finding a delicate balance of detail. Our readers are physicists. They're interested in the details of the experiment and the significance of the results. They may even want to see an equation or two. But remember, this still isn't an academic paper. If you're writing about biophysics, a string theorist should be able to understand it without too much problem. That means avoiding jargon and fleshing out any details that a technical paper might take for granted. When I was writing my honeybee piece, that balance wasn't too difficult to strike. But when I wrote a story about Io, which is Jupiter's closest Galilean moon, I had a bit more trouble. Astronomy is my native field, so it just took more work to step back and judge what other physicists might already know and what they might need explained. Our readers also are interested in seeing the data for themselves, and that often means including a plot as one of the figures. If a plot is straightforward and sheds light on your results without adding extra layers of confusion, then it can really complete an article. So once the first draft is written, it then gets sent to the editors. Usually 2 or 3 people will read over a piece and then send it back with comments. Lots and lots of comments. These initial edits are focused on content. So this is the step where the article really gets smoothed out and becomes a coherent and digestible story. And that's when it gets sent to the copy editors, who pound out any last technical issues in the writing, namely grammar. Lastly, the article goes to the contact scientist, the same person you had interviewed. Their job is to fact check. And this final step assures that you don't mislead the reader. but you can't give the scientists too much agency to edit, because you're not writing for them, you're writing for the reader. And once you're done filtering through the scientist's suggestions, the article is ready for publishing. This is definitely the most exciting step because you get to see the hard work pay off. I'd say it's a bit like publishing an academic paper, but you can send the link to friends and family and they'll actually read it. I'm still new to the world of science journalism, and I'm still developing my voice as a writer. But I've already come so far through this internship, and I'm really excited to see where it takes me next. I'd like to thank Andrew, who's been an incredible mentor this summer, as well as Kayla, Brad, and Michaela for all the hard work that they put into making this experience valuable. Thank you.
Wonderful job, Samantha. Quick question for you. If time, money, and space were no object, what would you most like to write about for PT?
Oh, that's a good question. Time, money, and space were no object. Well, I really love astroparticle physics, so if I could learn more and more about that, I think that would be my go-to.
I encourage that decision. So thank you for a great talk. You did a great job.
Thank you.
Yes, thank you, Samantha. We have one more talk before we take a quick break, and we'll be right back for more presentations. But up next, we have Hale Stolberg from the American University, our AIP FYI Science Writing Intern.
Okay. Can you see my screen?
Yep, it looks great.
Okay. Okay. Hi, my name is Hale Stolberg, and this summer I had the pleasure of interning at FYI Science Policy News from AIP. When I was first given this opportunity, I was incredibly excited, very nervous, and dealt with a lot of... There's no way that I, a physics major with no journalism experience, mind you, was going to write for a highly respected news outlet. I'm here to tell you that it's not as bad as you think, especially with great mentors, excitement for science policy, and a lot of help. So my presentation today will cover three things. What is FYI? What does FYI do? And why is the work that we do important? In short, FYI is an authoritative news and resource center for federal science policy. What's federal science policy? Any action, directive, bill, legislation that affects scientists, researchers, and science students that the federal government takes. Usually that means NASA, the National Science Foundation, the Department of Energy, etc. It's all science policy, and FYI covers it. On a day-to-day basis, FYI is run by these lovely people, and I'm so grateful for all the help, patience, and the trust that they've put into me. Mitch, Adria, Will, Andrea, truly, thank you. At FYI, I would say that we have three main products: a weekly newsletter, bulletins, which are long-form articles, and trackers for budget requests, bills moving through Congress, and leadership at executive agencies. Over the summer, I've contributed to each of these products. I was able to write a bulletin about space nuclear technology and how NASA and the Department of Energy are collaborating to put nuclear power into space. I was able to update descriptions on our bill tracker, and over 9 weeks, I wrote 18 blurbs, which is about 3,000 words for our weekly newsletter. I'm not going to go into the detail of the process. I think Sam gave a really good overview of that. I will say, though, that her editing section is extremely accurate, and that there are at least 6 versions of my bulletin sitting on my computer, all with enough red ink to make it look like a scene from Carrie. So enough about me. Why is the work that we do important, and why does it matter for undergraduates? My first point is communication. Physics as a field, and especially undergraduate physics education, does not put enough emphasis, if any, on communication. Heck, I've never even taken a communications class. One of the biggest things working in science policy and writing for FYI has taught me is how to communicate about complicated policy topics clearly and succinctly. The average FYI reader, whether they be the head of a federal agency or just a curious student, shouldn't be expected to know every single topic in science policy, nor be subjected to a lengthy explanation every time we bring something up. Learning how to strike that balance is the key to communicating clearly, and something that is applicable to physics as well. This chart shows that PhD scientists, as well as politics-trained professionals who work in science policy, what they believe are important for the field. Notice that communication is universally agreed upon as highly important. These skills serve physicists well, especially when they write and present research. Another point is that policy affects undergraduates. Recently, Immigration and Customs Enforcement, ICE, issued a policy that international students with valid student visas would be denied entry to the United States if their schools were all online. ICE has since reversed course, but is still barring freshmen with this status from entering the US. If you were an international student, keeping up with and engaging with these policies would be critical for your future studies. Similarly, if you are a senior out there thinking about applying to grad school, myself included, the NSF has recently issued specific focus areas for their Graduate Research Fellowship Program, GRFP. The foundation has been a bit cagey about answering if applying with one of these focus areas would increase an applicant's chances of being funded or vice versa. If you're a senior applying to this opportunity, an NSF decision would have major consequences on if your application would be accepted or not. So I think I've made my point about why engaging with science policy is important for undergrads. Now you might ask yourself, what can I do? There are the usual things. Being part of a society like SPS and APS, lobbying Congress, and contacting your representative are all great starts, but there's so much more. You could intern on Capitol Hill like Paul and Kyle. Not everything has to be about federal science policy. Not everything has to be about federal science policy, and you can talk with state and local lawmakers. Newspapers and other publications rarely get to hear from undergraduate scientists, especially those wanting to talk about politics. Good science policy practitioners know the science, but also have to understand how the government works. If you're interested, take a politics or a civics course for your gen ed. And lastly, maybe the hardest, network. Science policy has really taken off, and some networks like the National Science Policy Network are beginning to grow. Go on Twitter, follow some influential people in the field, reach out and see if you can conduct an informational interview with them. You'll be surprised how much people are willing to talk about themselves. So I hope my presentation has showed what I did this summer and why it's so important to keep on doing what we're doing. Thanks.
Thank you very much. I appreciate you. Quick question for you. So you mentioned informational interviews. We have some of that in the SPS Careers Toolbox. If you had to give one quick piece of advice to somebody who's going to do an informational interview, what would it be?
I would say, the point of an informational interview is to get somebody else to talk about themselves. You want to be very friendly and also make sure that you're actively listening, that kind of thing. And again, an informational interview, the point isn't that you are looking for an opportunity, it's just to get information. So make sure that you're respecting their time.
Awesome advice. Thank you again, and you did a great job on your talk.
Thanks.
Thank you so much, Hal. So we are going to take a very quick break. We will resume back at 12:25 Eastern time with a talk from our SOC intern. So we will see you in about 5 or 6 minutes.
Hi, everybody. I'm Brad Conrad. I'm the director of the Society of Physics Students. Just giving a little brief intro for the second part of our session today. Just as a reminder, this is the SPS 2020 Virtual Internship Program Symposium. I want to thank you all for joining us. I know it's taken time out on a Friday. I really do appreciate you being here. Just to highlight, the internship program is 10 weeks long. It's funded by AIP, the American Institute of Physics, and through donations from Sigma Pi Sigma members and friends of the Society of Physics Students. This internship program, in my opinion, is one of the most important things that we do. We've had 16 interns this summer, and we had to do it virtually because of everything going on, but it was a giant success. And so, as you can see here, the breadth of presentations is spanning all different topics, and they all had quite different experiences and mentors and projects and programs and things that they accomplished. But the thing that brings it all together is that they shared together their experiences and everything they were able to do. So I just want to thank you all, A, for joining, and B, for supporting the students that are presenting today.
Awesome. Thank you so much, Brad. So we'll go ahead and get started with our next talk. Thank you and welcome back. We have Holly Fortner from Marquette University, our AIP SPS SOC intern.
Hi everyone, I'm going to share screen real quick. Okay. Kayla, can you see and hear me okay?
Perfect.
Okay, thank you. Okay. Hi everyone, my name is Holly Fortner and I'm the SOC intern or Science Outreach Intern for this summer. This presentation was made in collaboration with Brad Conrad, who's my mentor for this summer. And today I'm going to be talking about sharing physics through sound via undergraduate outreach. So what is outreach and what is the overall goal of outreach for SPS? Typically outreach is used to share excitement on a certain topic and maybe even potentially open career pathways for people. But for SPS, the overall goal of outreach is to share physics and astronomy with younger generations and present undergraduate students with planning and leadership opportunities, as well as a sense of service. And SPS has been so successful over the years with outreach that it's come to help over 100,000 kids per year. So SPS offers 3 different categories of outreach on their outreach webpage. And first off, we have demonstrations, which are science activities that are very comprehensive for different age groups. And they're perfect for at home or for SPS chapters to do in the classroom with students. Next, there's Jeopardy and Trivia, which are physics and astronomy related games and activities, but there are also customizable templates that you can download and maybe play with your SPS chapter. And last but not least, the thing I've been working on all summer, which is the SOC, or the Science Outreach Catalyst Kit. And this is a free resource for SPS chapters to use during their outreach activities or events. These are all of the demonstrations that are posted on the SPS webpage. And as you can see, there's quite a few different categories that you can get involved with if you're interested in getting more involved with outreach. The ones that are highlighted in, or not highlighted, but outlined in dark blue are what have been posted so far. The 3 on the right are demonstrations that I posted, and the 2 on the left are SOC demos that will be included in the SOC, but also included online. I must say that I've had some really helpful volunteers this semester, or this summer, with demonstrations, so I'll be adding more very soon. One of the demonstrations that I've posted online recently is called Passive Pasta. And this is a great way to show different age groups how to conserve energy via passive cooking. And it basically just involves using an insulated travel mug, hot water, and noodles to cook spaghetti while conserving energy. And it's great because it took less than $20 to put together. And with only using household or easily accessible items. Another demonstration that I posted is called Ice and Salt Slushies. And this is a super fun activity for especially parents and kids to do at home during the summer on a hot day. But again, this demonstration was less than $20 to put together using common household items. And like all of the other demonstrations that are posted on the SPS webpage, there is a write-up available, which is basically just instructions on how to put the demonstration together, as well as physics explanations that target different age groups, such as elementary and middle school, and even high school ages. The crown jewel that we've been working on all summer is called the Science Outreach Catalyst Kit, or the SOC. Like I said earlier, it is a major free resource for all SPS chapters, and it's designed for all chapters. So whether you are just now getting involved in outreach, or you are an outreach pro, this resource is for you. And it contains 1 or multiple science activities that you can do during your outreach events. So specifically for the 2020 to 21 SOC, the theme is it's themed around the International Year of Sound, so we have acoustics demonstrations included in this SOC. Not only is the 2020 SOC supported by the American Institute of Physics and the Society of Physics Students, but also the Acoustical Society of America, which has allowed us to increase our usual 100 kit count that's available to only SPS chapters. We've been able to increase it to 200 kits, and it will then be available to both SPS and ASA chapters to do during our outreach events. And this year, the activities that will be included in the SOC kit will be one demo is the portable oscilloscope and microphone demonstration, which just includes a little portable oscilloscope that you can see in the picture below with the handheld, more durable microphone for small children. And this can just help you visualize sound waves, and as well as the waveform and spectrograms that we are putting together from a recording software in Audacity. So we'll be able to show children their voices via sound waves. And we also have a demonstration that will be using a slinky and a tuning fork to visualize these sound waves. So using a slinky to create both transverse and longitudinal waves, and dumping a tuning fork into a bowl or cup of water to see the sound waves ripple away. As we'll also have other resources like soundscapes and insightful and engaging diagrams to help teach the students about how we hear, what sound waves really are, and as well as more detailed speech exercises so you can view different waveforms on the oscilloscope. Okay, and that concludes my presentation. I just want to say a quick thank you to SPS as well as my fellow SPS interns, Kayla, Michaela, for making this program happen this summer, Keita Jones, and last but not least, my mentor, Brad Conrad, who's been very supportive this summer. So thank you again.
Great job, Holly. Quick question for you. With topics like astronomy, optics, and acoustics, did you work with AIP member societies to create the SOCs?
I worked solely with Brad, really, to put this together. So I'm not sure how to answer this question. I mean,
we worked with Keita, right? Because Keita was.
We did work with Keita. Yeah, I'm sorry.
And several of Keita's volunteers, which are ASA members.
Yes, okay, thank you. Yes, we did work with Keita, who's a linguist from the Acoustical Society of America, as well as two lovely gentlemen who helped us along with soundscape resources and microphone resources for the SOC kit.
So great. Thank you so much, Holly. It's been a pleasure working with you, and you did a great job on your talk.
Thank you.
Yes, thank you, Holly. Up next, we have our Society of Rheology and AIP Niels Bohr Library and Archives intern, Abigail Ambrose from the College of Worcester.
Can you see and hear everything okay?
Looks great and sounds great.
Thanks. Hi, everyone. I'm Abigail Ambrose, and I recently graduated from the College of Worcester in Worcester, Ohio. And this summer, I got to work with the Society of Rheology and the Niels Bohr Library and Archives to write biographies for the Society of Rheology Fellows. So, to start with, what is rheology? It's the study of the flow and deformation of matter, which is not something I was familiar with prior to hearing about this internship. So my goals for this summer included condensing Bingham Medal biographies, which were written by the past two interns for the Society of Rheology through SPS. And we were condensing these to the length for the fellowship biographies, and then I wrote biographies for the remaining fellows and found photos for any medalists who did not already have photos. So the Society of Rheology Fellowship began in 2015, after a conversation by the executive committee and a vote by membership, and it serves to recognize distinguished scientific achievement, technological accomplishment, or scholarship in rheology, and a heavy look is done to the service with the society. Only 5% of the Society of Rheology total membership can become fellows, and at any given year, only 0.5% can be elected, and fellows become emeritus fellows at the age of 75. So down here's a photo of the inaugural class from 2015. So in 2015, started out with 36 fellows, and then each year after that, 7 have been added. So this is the photo from the 2016 class, and then 2017 and 2018 photos for all of the fellows at the annual meeting. So I'm going to go through some of the examples of people I worked on. So to start with, I worked on Gerald Erickson, who was awarded the Bingham Medal in 1968. He worked at the U.S. Naval Research Lab prior to working as a professor at the University of Minnesota, and he studies the flow of liquid crystals and continuum mechanics, and is an honorary member of the Royal Irish Academy. And along with all of that, outside of physics, he enjoys a good party and woodworking. Next, I have Andy Kranick, who I actually had the opportunity to talk to about his biography. He served as the secretary of the society from 1989 to 1999 and the president from 2005 to 2007. He won the Distinguished Service Award in 2001, which is an award given at the discretion of the executive committee, and it's given quite rarely. And he has attended every Society of Rheology annual meeting since 1977, which I'd say is quite the accomplishment. And he's known as the leading authority on rheology of films. And in his retirement, he has enjoyed going on trips to Central and South America to go birding. So I got a few pictures from him from his most recent trip. Next, I have Faith Morrison, who served on multiple committees for the Society of Rheology and is still a very active member. She served as vice president from 2009 to 2011 and president from 2011 to 2013. And she is one of the few women fellows for the Society of Rheology. And along with research, she's very interested in pedagogy because teaching is very important to her and has written 2 books about the matter. And she received the Distinguished Service Award in 2015. Finally, I have Robert Mendelson, who passed away in January 2020, unfortunately. But he actually is originally from Cleveland, Ohio, and as an Ohioan, I'm quite proud of that. He worked at Monsanto Chemical Company and Exxon Research, and served as the secretary of the society from 1973 to 1977 and the president from 1989 to 1991. And during his presidency, he worked to halt regulations that would have prohibited federal employees from serving on executive committees of scientific societies, which is of particular importance to the Society of Rheology because many members of the executive committee are from the National Bureau of Standards and NIST, so it would have done a great deal of disservice for the society. So some things I learned from my internship this summer. The archives are both an interesting and a tedious place to look for biographical information. I went through the entire folder of Mendelssohn's correspondence, and it was a lot of information about everything from reimbursing MIT for food that they got for a meeting, and also his information about halting the regulations. Rheologists come from a wide variety of fields. There's engineers, physicists, mathematicians, and many other fields. And industry work also varies widely. I've seen work with Coca-Cola, chocolate, foams. It's incredibly diverse. And finally, remote research is very hard. There were many times I wanted to just be able to go look through those folders myself, but they're in Maryland and I'm in Ohio, so I couldn't. But I really enjoyed working on this still, even though it was so difficult. Quick summary, I distilled 21 of the Bingham bios in total, edited 5 biographies that were partially written, and wrote 6 biographies from scratch, and they'll all be posted at the Society of Rheology Fellowship page. Quick thank you to my mentor Gareth McKinley at the Society of Rheology, the Niels Bohr Library and Archives, and everybody there who's been so incredibly helpful, and the SPS programs, and of course, Brad Conrad.
Thank you very much, Abigail. Couple quick questions. Does the fact that Coca-Cola works with rheologists mean that they're working on non-Newtonian beverages?
I wish, but I don't believe so. I would love it if that's what they were doing, though.
And one quick follow-up question. Do you have a favorite thing that you learned about the field or study of fluids?
That's a good question. I really liked how diverse it was. When I first came in, I didn't really think that it would be as diverse as this, and I liked how much interesting industry work was an option, which I didn't really think about. So not too specific, but I just liked how different everything was, and I frequently came across surprises as I was reading.
Wonderful. Thank you for a great talk. We really appreciate you.
Thank you.
Yes, thank you, Abigail. Up next, we have our AIP Center for History of Physics and Niels Bohr Library and Archives intern, Maria Stokes, and from the University of Utah.
Thanks so much. Hello, everyone. My name is Maria Stokes, and today I will be discussing omitted history, and in particular, how it can be included in education and an outreach avenue that I focused on this summer. As a form of introduction, I want to look at a quote from Moses Refkin in his article, Addressing Underrepresentation, Physics Teaching for All. And he wrote, quote, "When we teach physics, we talk about physicists, Newton, Maxwell, Lenz, and Einstein. We take time in our classes to name and sometimes discuss who has done the physics we are teaching. Whether we realize it or not, most of us implicitly communicate to students that scientists come from one demographic group. But there is a richer history of physics among other groups than shared by traditional presentations of physics," end quote. It was with this in mind that the Center for History of Physics at AIP began to develop teaching guides that present undertold stories. These teaching guides highlight contributions from individuals underrepresented in physics. Each of these guides follow the 5E teaching model and are made using resources from the Niels Bohr Library and Archives. There are currently over 50 guides available online. My first task this summer was to develop new teaching guides, and I wanted to take a slightly different approach than some of the teaching guides of the past. And in particular, I wanted to connect historical topics to significant physics topics. And this decision was motivated by my experiences as an undergrad. As an undergrad, I majored in both physics and history, and I also took some classes in pedagogy and physics education research. In the process, I realized that some physics professors wanted to include short segments of history regarding physicists from underrepresented groups in their classes. However, the applicable sources are not always easy to find. I realized that my background, as well as the work that the Center for History of Physics at AOP was already doing, made this a perfect opportunity to address this need. So I started developing my teaching guides specifically focused on introductory physics, as well as historical enrichment. I also wanted my teaching guides to be available to both high school and college groups. And though this wasn't the initial intention, I developed visual elements along with each guide. So in total, I completed 3 new teaching guides, 2 of which are now available online and the third which will follow shortly. The first is on the shoulders of giants, and this introduces the law of inertia while highlighting the contributions from scholars in the Islamic Golden Age. Much of the work in between the 8th and 13th century in the Middle East was done on topics in natural philosophy, including motion, and really laid the groundwork for the understandings of motion that came out of the scientific revolution. The second topic that I focused on was the four fundamental forces. told through the life of Dr. Abdus Salam. Dr. Salam made contributions to unifying the weak force and electromagnetic force, and he became the first Muslim Nobel laureate in physics. And then finally, my last teaching guide communicates the benefits of multi-wavelength observations and looks at the life and work of Dr. Franz Cordova, former NASA chief scientist and the first Latina director of the National Science Foundation. I wanted to briefly highlight some of the historical enrichment sections in these teaching guides. I recorded biographical presentations for both Dr. Salam and Dr. Cordova, and these can be easily implemented in the physics classroom. I also made a visual timeline for the teaching guide on the shoulders of giants, and this presents developments in the history of physics from both the Middle East and Europe to really contextualize the timeline. I also used processes very similar to what appears in other teaching guides already available, and those are handouts and discussion questions. And then finally, I made use of some of the oral histories in the Niels Bohr Library and Archives conducted by the Center for History of Physics that spoke about the life of Dr. Salam and added some more history. On the other side, looking at the physics content, I repurposed the video I submitted for the SPS demo competition because it had to do with inertia. And I also left tips for instructors who want to use it in their classroom. I also compiled media, so the images of the Andromeda Galaxy I put together to help visualize multi-wavelength astronomy. And I also put together lecture outlines for instructors who would be working outside of the scope of their textbooks if they implement these teaching guides. At the same time, I also was working on outreach. So a lot of the media that I have discussed was actually developed with outreach in mind, and I later incorporated into the lesson plans. And there was a lot of nice overlap because the areas I was researching were the same for both projects. The main avenue I examined was the Niels Bohr Library and Archives and Center for History of Physics blog, Ex Libris Universum. And I wrote 5 posts for that, one of which is available online. The blog post that is available is a visual walk through the fundamentals. And this was motivated by the fact that one of the primary audiences of the blog are those with backgrounds in archival science, but who are looking at physics. So I realized that this was an ideal place to look at physics communication while highlighting some of the material from the collections. In particular, the visual archives have over 30,000 images. And so I pulled from some of that material and told physics as a narrative, focusing in this case on unification. So as a summary, this summer I focused on communicating physics through images and narratives. I explored new avenues and directions for the Center for History of Physics teaching guides and compiled material on undertold stories that introduce introductory physics topics. And then finally, I also drew awareness to physics through AIP platforms. Thank you so much for everyone who has helped and guided and supported me through this work. And I am happy to answer any questions.
Great talk, super well done. Quick questions for you. First is, what is the 5E teaching model?
Yes, the 5E teaching model focuses on engaging, exploring, elaborating, evaluating, and I missed one of the E's, I'm so sorry. But essentially it has this process of slowly introducing the medium through both students learning it themselves as well as explanation, and then finally assessment, so.
Okay, and one more quick one. Are these teaching lessons applicable to online teaching?
Yes, I think that they can be incredibly useful during online teaching because there is so much digital material supporting them. Obviously there's not a whole lot of experience with that for these guides in particular, but I think they may be very helpful for developing that new online curriculum that we're all looking at now.
Great job, wonderful talk, and thank you for your presentation.
Thanks so much.
Thank you so much, Maria. Up next, we have Ben Pecky from Rochester Polytechnic Institute. He was the American Association for Physics Teachers intern.
All right, thank you for the introduction, Kayla. Okay, so my name's Ben Petke. I was the summer AAPT intern, and something I really got to notice over the summer was the inequality in the physics community. A few other presenters have talked about this, but I'm gonna focus mostly on women in physics. I thought STEM was really moving in the right direction with social justice, but there's obviously some work we need to do, and I'm gonna share some resources and things I did to try to push this forward. So what I want you guys to take away from this is that women in physics are underrepresented, other minorities are. There's data to show it, I'll show you it, to highlight it. And I want this to be shared as far and wide as possible because I think the data is very shocking and it really gets people thinking about it. I want to show you guys ways you can contribute to the cause with art and media, as I did, as I'll explain later, and learn about different organizations who promote equality in the physics field. And finally, I'm going to showcase some side projects I worked on during my internship that are not quite related to this, but still very fun. So a quick data chart. This is undergraduate women by major. So it shows the percentage of women who earn degrees by major here. So the line at the top that's brown is biology. So they're around 60% in biology. But disappointingly enough, purple, which is engineering, and red, which is physics, are both hovering around 20%, which is something that really needs to be changed. And there are places doing things about this, which include Step Up, who I worked with a lot. So here's the full chart on everything, all of the majors and such. And like I said, they're trying to get the graph a little more evened out. So they are a federally funded grant, and they obviously promote equality for women. And what that includes is recruiting Step Up ambassadors who are high school teachers and college teachers who are provided with lesson plans to give during their classes. So there's a lot of resources given to them. And some of the lessons include women in physics, careers in physics, and everyday actions to promote equality. There's been great feedback on these things. Students love the careers in physics. That's a great way to spread the word. And also they get paid for it as well. So there's a great motivation to do it, as well as just obviously spreading the word. And the students seem to love it as well. So how was I involved with them? I actually created a podcast this summer with the help of Mark and Justine, who made the cover art and recommended some of the music. And I did it on Step Up, where I invited 3 student ambassadors from Texas A&M as guests and talked about what Step Up's all about and some of the things they did, the research they're doing and projects they're working on as undergraduates. It was really fun to make this, and it's really not that difficult. You can edit and post it using all free software. You can post it to Spotify for free, all this stuff. It doesn't need to be someone super high profile. I talked with the 3 students. It wasn't someone who was super well known, but you treat it like a topical discussion with some questions ready on the side, just in case conversation slows down. So what I'm getting at is you can spread the message in fun and creative ways. It doesn't have to be a podcast. There's painting, graphic design, digital media, and just spreading the word like in this next slide here. So maybe that isn't quite your cup of tea. Like I said, spreading the word on the facts and everything can be really helpful, but there are some resistance you're gonna meet. For example, Maria actually talked about him, Moses Rifkin, who is shown in this image here, developed a 6-day curriculum essentially on white privilege and underrepresentation. It was 6 days of the year. And there was a whole segment on a news channel about how he's not teaching physics in a physics classroom, and that's why we're falling behind in physics. So obviously there's still a ton of misconceptions, really upsetting to see these kind of videos. And hopefully, and if you look at the student perspective, which is on this next slide, they loved it. They thought it was super helpful. The district supports him. Stuff like this and people say it's so bad, and they have arguments against it, and they say he was jealous of the other teachers. I think it's ridiculous, and that these obstacles need to be overcome by just spreading the word. And so there are other people involved, other organizations and groups involved in trying to even out those curves. So one of them is the Underrepresentation Curriculum Project from AAPT. and you essentially fill out a survey and get access to a bunch of lesson plans. Here's just a quick overview on the slide. It's really fantastic. They focus more broadly than just women. There's a lot of racial inequality things in here as well, which is really awesome to see that there's more. So what you guys can take away from this, and what I'd love you to do is each and every one of you just share some information from the talk with someone who might not know these things. It's very surprising to see that women are only 20% represented in physics undergraduate degrees, and spreading that word can really get it out, and it can lead to such a great outcome. So going into a slightly different topic, which was some of the other things I worked on, were more for distance learning, which included a student panel that I got together for the AAPT summer meeting, which was extremely fun. We ran a high school physics lounge. The student panel I put together was from a high school that was local, and they talked with teachers about how distance learning was affecting their learning and talked about some ways they think they can make it better. And the commercial I made was for the AAPT Ground Challenge, where people would send in tactile at-home labs students could do. It was a really fun commercial to make, and we got a good amount of submissions that will be shared on the AAPT website. So thank you to everyone, especially Mark, Justine, Brad, Kayla, and everybody who could make this possible, and I will take questions.
Great job. Super awesome. First question, obvious. Are you thinking about becoming a teacher?
Yes, I am actually. I'm planning to be a high school physics teacher. I was slated to start in the fall for student teaching, but under current circumstances, I'm not sure if I'm going to move it or not yet, but I'm very excited. And yeah, I am.
Okay. Second question is, so you got to work really and learned about all the awesome resources. Was there anything that you picked up that you think will help you do a better job teaching when you do start student teaching?
Oh, absolutely. So, I mean, all those resources I picked up, like from Step Up and stuff, really shows me how to cater to my whole classroom a lot better. And just putting together like the panel and everything, I don't know, I feel a lot more comfortable with students as I got to interact with them a lot, and interacted with a lot of high school teachers, made so many connections at the summer meeting that I just feel like are invaluable. And I have them all written down when they asked me to. They said, I can help you out if you need. And so it was really great to just meet everybody, and I feel so much more prepared for teaching.
Well, you did a great job. Thank you for your presentation. We really appreciate it.
Thank you so much, Ben. Up next, we have Alex McCulich from the Colorado School of Mines, and he was our NASA research intern.
Sorry about that, I was muted. Hello, everybody. My name is Alex Mikulich, and I did my my NASA internship at the Goddard Space Flight Center. And today we're going to be talking about LDI mass spectrometry, which is very useful for finding the molecules that you have of a sample. Now, the way that works is that researchers are going to go ahead and shine a laser beam onto a sample of analyte, and this laser beam will desorb and ionize the molecules, and then you can find the composition of them. You can find the charge to mass ratio and then determine the mass. Now, this is pretty useful for several applications here on Earth, but it's also useful for future space missions where we can find organic molecules in our solar system. Now, LDI stands for laser desorption ionization, and it really works best when you have a homogeneous distribution of analyte. Because if you don't, your mass spectrum is going to be pretty inconsistent, and you won't be able to draw accurate conclusions about what's in your sample. Now, we also prefer small spot sizes to reduce the time that it takes to analyze them. So let's talk about the current method that we use. So we use what's called a dry droplet method. Now, what this does is you put the analyte within a dropper in a solvent, you apply the solvent onto the surface, and then you let it dry, and then it leaves behind the residue. But as you can see right here, that doesn't always work because liquid, when it's in droplets, it doesn't like to dry evenly. If you think about the geometry of a droplet, it's going to evaporate faster at the edges than at the center. Now, this leads to a current within the droplet, and this will then apply the solute at the edges in rings instead of evenly. Now, this is called the coffee stain effect. And it's also difficult to get small spot diameters. When we dropped on stainless steel, liquid likes to spread out. And this droplet that you see right here in the image is about 3 millimeters wide, which is about the smallest that I could get. And we're looking for like about 500 to 2000 microns, which is 0.5 to 2 millimeters. So I went ahead and tested this. I want to say, well, what could I possibly do to improve both the homogeneity and the spot size? Now, I use rhodamine as a substitute for analyte because it's very sensitive to UV light. It's very easily detected. And I also decided to alter several different variables, such as the solute concentration, solvent type, target plate temperature, droplet volume. I just tried to see what do I possibly need to do to get homogeneous in a small droplet size. And I also repeated this with an airbrush using a stencil. So I went ahead. So the dry droplet data, let's talk about this. Basically, the key takeaway here is that you cannot get a small spot and a homogeneous spot using this dry droplet method, because this coffee stain effect is really inevitable. No matter what you do, you can use a hot plate, you can use different solvents. You can also try reapplying the droplets on top of other droplets to fill the cracks. That also didn't work for me because every single reapplication is going to coffee stain on its own. So you really cannot use this method to have accurate LDI mass spectrometry. So I went ahead and tried an airbrush. And as you can see from the top right pictures, it looks a little bit more homogeneous from a distance. And that's because an airbrush will atomize the individual little droplets and then apply them onto the surface. However, it appears that once they get onto the surface, they start to coalesce. They start to form mini droplets of their own. And then this doesn't really improve the homogeneity. If you decided to do LDI spectrometry, you're still going to notice these spectrum inconsistencies, and this will not give you a decent, any reasonable conclusions that you could draw from. However, until you add the secret ingredient, which is heat. Now, when you heat the target plate, it appears that it will, instead of allowing these droplets to spread around on the plate and group together, it will evaporate them as soon as possible. As we can see in the top left, when we don't have any heat, the droplets like to spread around. They get a pretty sizable spot diameter, but also the individual droplets inside are very distinct. This is not homogeneous at all. But the minute that we add heat to this, it starts to, it was like I said, it starts to evaporate the droplets. It does not let them spread around on the plate or coalesce together, and therefore you get a homogeneous spot. It's also worth noting here that if you add too much heat, like in this bottom right picture, it appears to boil the droplets too violently, and it won't let you deposit them very homogeneously. So there's definitely a clear window in terms of the heat that you should be using. Now, I'll go ahead and leave you with this image right here. Both of these images on the left and the right, they use identical amounts of rhodamine, 250 nanograms. However, on the left, what I used was the dry droplet method on a room temperature plate. And we can see that it really likes to spread around. It's not homogeneous. It forms a ring instead of a spot. The spot size is not constrained at all. It leaves the scope of this it leaves the range of this microscope. So this is 4 or 5 millimeters in diameter. If you did LDI mass spectrometry on this spot, you would not get good results at all. But if you did it on the spot on the right, you can see not only is it very constrained, it's also a nice, even, homogeneous spot. Now, this one on the right, I used an airbrush. I used isopropyl alcohol as a solvent, which is more volatile than water, and I airbrushed this onto a 100-degree hot plate. So it looks like when you follow all of these guidelines, this is the secret to getting clear samples that you can then perform LDI mass spectrometry on. Now, ultimately, we can conclude from this is that airbrushing with the sample plate and with volatile solvent is the best way to improve both homogeneity and spot size for LDI mass spectrometry. However, it's also not going to be perfect. There are some noticeable drawbacks. Most notably, it's harder to calculate the mass of the analyte that reaches the plate when you're using an airbrush. Airbrushes are not as precise of a tool as, say, micropipettes, which I used. So if you do use this in the field, you're going to want to use a much more expensive and a much more precise method of delivery for the solvent. It's also worth noting that if you have a hot plate and you're trying to find out organic molecules, hot plates do tend to break them down. So you're going to have to carefully understand the analytes that you're looking for to make sure you don't destroy them with your hot plate. So that concludes my presentation. Thank you very much for listening.
Great talk. I had one question. So so when you're depositing this materials, how sensitive is it to the material as opposed to the solvent?
So I tried a few different materials, such as a few organic molecules like saccharin. I also tried Epsom salts, and then obviously you see here with the rhodamine. And one thing that I found is that it's not very sensitive to the material at all. It doesn't, no matter what solute you have within your solution, it's going to coffee stain and it's going to kind of distribute the same as if you were using rhodamine. So I did do some tests to find several different solutes. However, it was the rhodamine is most visible here. So that's why I used it in my presentation.
And you use the same kind of stainless steel for all of your studies, correct?
Correct.
Great. You did a wonderful job. Thank you for your talk. I really appreciate it, Alex.
Thank you. Happy to answer any questions in the chat.
Thank you, Alex. Up next, we have Anna Murphy from Rhodes College, also a NASA research intern.
All right, hey everybody. Going to share this screen. All right, are we live?
Looks great.
Perfect, okay. So, hi everyone. My name is Anna Murphy. I am a senior physics major at Rhodes College. And this summer I got to intern with Dr. Yaping Zhou at NASA Goddard. And we studied the controlling mechanisms of extreme precipitation events. So let's start with some background. So extreme precipitation events, or EPEs, are basically big storms, and these can cause major hazards like flooding, erosion, and landslides. And as our climate changes, we are expecting them to become more intense and more frequent. So we would like to study these and be able to better predict them. And the database of these events that we used was developed by my mentor in previous work from the iMerge dataset, which is a large dataset that combines data from different precipitation satellites. There's an example on the right. And to get more information about these events, we used the MERA2 dataset, which combines data from different satellites. And it has many meteorological variables available, both 2D and 3D levels. And it has data going all the way back to 1980, so it's a lot to work with. So the goal that we had was to correlate the characteristics of these events, such as their duration, volume, area, propagation, and more, with meteorological variables, such as specific and relative humidity, wind speeds, temperatures, and other variables available in MERA2. So for each of these variables, we wanted to collect an area around the event's central point, and the size of that area we scaled relative to the event's duration. So for shorter events, 0 to 6 hours, we collected 5 by 5 degrees. For medium events, we collected a 10 by 10 degree. And for events longer than a day, we collected a 15 by 15 degree grid. And that's just because larger events tend to be longer and we want to capture as much of the event as possible. So we collected these grids at 5 different time steps around the event. So 12 hours before, at the start, peak, and end, and then 12 hours after the event ended, capture the temporal change of these variables. And our approach to do this was Python. So I wrote a whole bunch of codes to locate and characterize these events. I also wrote some codes to compute seasonal trends and different variables. And I got to do this within the Discover supercomputer, which was really convenient because it's a lot of data. On the right, that's what it looks like when I forgot to remove the print statement and then ran it on 40 years of data. So the inputs for these codes are the event statistics from iMerge, also the MERA2 data files. And the outputs are new data files with each event's information, and also maps of these variables and scatter plots of their averages, things like that. So here's an example result of locating an event. On the left, you see the precipitation of an event from spring 2017 from the iMerge set. And so you can see it's a pretty large system. Starts down in the southeast and then moves pretty much up the whole east coast. And then on the right, you have maps that my code made. So we have the humidity measured at 4 different vertical levels here. We also have the eastern wind and the northern wind. And as you go down this figure, the time is increasing, but there's a lot going on here, so I want to focus on something that's pretty clear. So the 850 millibar humidity, you can see that the values track pretty well with the peak time, and then as the storm progressed, you could see it move off of the coast. So that's pretty nice. So from there, we wanted to average those grids that we collected and plot a bunch of variables against different event characteristics. And we were hoping to see some clear trends, ran this on a whole season of data. Here's an example. There's 2-meter temperature versus the event duration. But as you can see, there's not really a clear trend going on. So all right. Did I freeze for a second? Okay, we're good? Cool. Okay, so next up, running on more data. So then we also wanted to put these events in the context of global circulation. So here's a map of global circulation in the spring season since 1980. And the contours plotted on top are basically how it's changed since then. So pretty nice. And from there, we took seasonal averages over the US to link this to the events that we were measuring over the US. And we found some slight trends in the summer and fall wind speeds. You can see these top 2 plots are from my code, and the blue and black lines are showing the wind speeds over the years. And the bottom plot is showing decreasing propagation of shorter events. So again, the blue and black lines are the propagation speeds of these events. And so we're thinking that these might be correlated, which would be cool. So in conclusion, I developed some codes that can locate these events, select different variables, and plot them in different ways. And I also wrote some codes that can collect seasonal trends in wind speeds or in other variables. But we'll need to do some future work to determine which variables best correlate, because there are a lot of variables to work with and a lot of events to analyze. But we do think that the seasonal variability in wind speeds might be correlated to the event's propagation speeds. So I'd like to thank Dr. Gerald, the SPS team, and my fellow interns, and NASA Goddard for making this happen. Thanks for listening, and I'll take any questions.
Great talk, wonderful. So I had one about your correlation. So you found a weak correlation, right? So my question is, if you were to use, and I think you had talked about how use different data sets that result might change. If you were to go back and redo it all over again, what's one thing you do differently?
I would start learning how to write faster code really soon. Yeah, I didn't really appreciate how much data this was when I started. So I was like, oh, I think it runs pretty fast, but each season has thousands of events in it. And, 4 seasons times 40 years, that's a lot. So yeah, I would optimize.
That sounds like a great plan. And one other question is, so if you were to get another, let's say, a couple weeks to work on this, what would you have done next?
Yeah, so next steps. So I didn't show it in this talk, but we also worked on analyzing the wind speed trends in different bands of latitude across the US. And we found some more significant trends there. So I would work on probably analyzing events specifically in those bands and see if those correlate. So,
great.
Yeah.
Well, thank you for your presentation, and thank you for the question answering. I appreciate that.
Thanks, guys.
Thank you so much, Anna. So last but certainly not least, we have our NIST research intern, Abdul Qadir Rehan.
Thank you, Kayla. All right. Hi, guys. My name is Abdul Qadir Rehan. And for the summer, I was working at the National Institute of Standards and Technology under the supervision of Brian Barnes. And we were working on applications of machine learning for defect meteorology. So what exactly is meteorology? It is the scientific study of measurement. And our particular challenge that we were looking at was 300 millimeter wafers on which we were inspecting sub 10 nanometer defects. So optical methods allow us technology which we can use to quickly take images of these wafers, but the problem we face is that the images are not resolved. So how exactly are we able to see the defect on these images? So we all know birefringence from our physics 132 classes, where basically due to geometrical differences on a material, it shows varying refractive indexes on within the material itself. So form birefringence basically is because of geometrical factors and structures on the wafer, which allow us to basically see that the defect is present at a certain location on the wafer itself. So the STM images of the defects are shown over here, and the defects are basically circled in red. So there are 4 different types of defects: X, Y, J, and A. And for my research over the summer, we were looking at all 4 of these. But we would hope that the defects would look like this, but in reality, through the optical microscope we were using at 193 nanometer wavelength, the images look like a gray block. The images were taken at 76 different Z depths. So this is basically images at different depths of the wafer itself. So yeah, we basically can't see the defect on these images. So we had to do a lot of image processing in order to do in order to feed it to our algorithm for it to classify whether there's a defect or not. So firstly, we do a Fourier transform to get the image from the spatial domain into the frequency domain. And then we do a Fourier shift to get all of the lower frequencies near the origin, and moving outwards, the frequencies increase. We apply a high and low pass filter, which allows us to get rid of the low frequencies and the high frequencies to basically dim and highlight certain features on the image that we want. And finally, we do a Fourier shift to get the image back to where it was. And finally, we have the inverse Fourier transform to get the image to somewhat look clearer. So now you might still be asking, like, where's the defect on this image? You can't really see that. Well, if you look closely at where the red arrow is pointing, you see a black dot over there, and that's the defect that we're trying to look for. To build a data set for my machine learning algorithm, we basically took 100 by 100 pixel squares for a no defect and a defect scenario, and we basically just shifted the box around so that we can basically cover all of the different scenarios where a defect might be present within the image. And we were able to make a data set of 270,000 images from this. So how does the machine learning algorithm basically take this image and predict and classify whether there's a defect on this image or not? So there's a whole bunch of stuff that goes on within it. But the main thing to take from this is that certain features get highlighted, and in our scenario, it's basically whether there's a defect or not defect, and that feature is basically exaggerated throughout this architecture within it. And in the final, the model is able to classify whether there's a defect or no defect. This architecture, like explaining what this architecture is, would be for another talk. So I'm not going to go into much detail about that. So moving on to the results. So we have a BY defect, a J defect, a X defect, and an A defect. So there are 4 types of defects. For each of the 4 defects, we had 2 dyes. For each of the dyes, we did 3 experimental repeats. And for each of the repeats, we had 2 linear light polarizations. So there was a vast span of data that we had to deal with to begin with. So we were able to train our model to classify each of the defects individually, and we were able to classify successfully the defects across repeats. So we're using repeat 1 and repeat 2. And one of the good things that we were able to do this summer was that we were able to identify A defects, which was not like as prominently done before. As you can see in the table, these are basically the accuracies our model was able to generate. So for within the repeat, when testing the images, we see that all of the 4 defects resulted in 100% accuracy, while across repeats, it's basically just 99 point a few decimal points, and we can almost count it as 1. And for those of you who might be a bit more familiar with machine learning and stuff, I've basically plotted the histogram, which shows the different probabilities for each of the images as to how the algorithm was able to classify them. So the threshold over there was 0.5. So anything above the zero 0.5 probability was classified as a no defect, and anything below the 0.5 threshold was classified as a defect. So that's my bibliography, and I'll be taking any questions you guys have.
Wonderful talk. Super awesome. And it doesn't hurt that I used to work in the research group that you're interning in. So I'll ask a quick question for you. Why are we really concerned about defects?
So the main issue that is coming right now is that we all know about Moore's law, that like the number of transistors on a chip is continuously increasing, but we're sort of hitting the thresholds where we can't really exceed that. But even at the point that we're at right now, the trouble that we have is that we're mass producing these chips, but we're not able to identify any particular defect because of the dimensionality of the defects on the chips itself. So just to give you a rough estimate, so the 42 states of the US, like the bottom 42 states, if you combine them, what we're trying to do is we're trying to find a football field within that 42 states. So it's a very big size in comparison to the defect size itself. So having a fast enough method to identify these small defects would allow a higher throughput.
Yeah, that's actually a really nice explanation. That was good. And we have one quick question. So you use this image processing technique. Were there other filtering techniques that you could have used, or is this kind of the only one you could use?
So Dr. Brian Barnes, I mean, he has been working on this issue for a long time. Some of the stuff that he had done earlier was not using machine learning techniques. They would just take images, shift the images up by 3 pixels, subtract the image, and through that, they were basically able to identify whether there's a defect present on the image or not. If anyone is interested, I can forward you the paper that Brian Barnes had published on that, and it's a good read.
Great. Well, thank you for a wonderful talk, Abdul. That was spot on.
Thank you.
Yes, thank you to all the interns that have presented. You did an amazing job. I would like to just, again, like Brad in the beginning, thank all the mentors and thank you interns, because we would not have been able to do this program without you. And we also want to thank all who support SPS and Sigma Pi Sigma through donations. We do have one presentation left, just a project that our stock intern Holly did, but I'll let Brad introduce her again.
So working for me isn't easy because sometimes I throw you curveballs or things that have never been done before. And so I tasked Holly with putting together a set of demonstrations that you could do at home in conjunction with the American Association of Physics Teachers, their annual meeting in the summer. So Holly, take it away.
Hi, everyone. So like Brad said, we put together a montage of videos. And these videos show demonstrations that all of our interns put together, and we turned it into more of a competition. So I'm going to present the video now. Give me one moment. I'm going to share computer sound. Okay. Let me know if you guys can't hear it.
Holly, can you turn your sound back on? Holly, just unmute yourself.
Do I need to start it over? Okay.
Just pick it up right where you left off. Just keep your sound on and turn it up a little bit.
Sorry.
So just yay, everybody, yay. And so that was a really fun thing. We had a lot of people vote on the competition to decide who the winner was. Holly, remind me, who was the winner?
I think it was Ben. Was it Ben? I don't remember.
No, I think I was second. I think Abdul won, didn't he?
Oh no, Abdul won, and then
Yeah.
Ben, you were
With the
second,
cooking. Then mine was in second.
and then Madison's was third. So yeah.
And just so the audience knows, there were cash prizes for this, or at least like little gift card things. So like the winners do get, we did make it a big deal, and it was nice that all of AAPT had a chance to vote on these and see these. So please take the video and share it around. And if you're looking for things to do because you're stuck at home or you have friends that are stuck at home, I put the link in the chat, and I'll do so one more time. Kayla?
Again, I just want to thank you all for being here. This would not be possible without our mentors, the support of AIP, and just so many working pieces to make this happen. So we're just extremely grateful, and that you all just stuck through and you were patient with us, and you were still here. So thank you again. And thank you all who came to the presentations as well and supported the interns. We really appreciate you. And we can just give everyone a round of applause. You did absolutely amazing.
Yay. No, seriously, you all did phenomenal. I can say this was a unique event. I would even say very unique, because the odds of it happening were pretty small, right? And you all did a wonderful job presenting. So I just want to thank you. Thank you for being an SPS intern. Thank you for sharing part of your summer with us. And SPS is always a home for you. You can always come back. We encourage you to come back to future intern presentations and share all of the wonderful things that you learn and see, because we're one big giant physics community. So I think that might be the end of it. So I hereby declare you all official emeriti of the SPS internship program, and you'll be hearing from us for many years to come. So thank you all for coming, and thank you for helping to celebrate this this good achievement that we had over the summer.